right? So we want molecules with a pi-to-pi star like we saw in oxygen. And the reason I showed you oxygen rather than something more complicated is because those molecular orbital diagrams get crazy complicated as we add more than 2 atoms to it. So we want that small energy difference between the pi and pi star so that we can get that excitation and see some fluorescence back out. Right? There are a couple things that help with this. Right? A couple things that are beneficial for us. So that's one thing. The second thing is the more rigid the molecules, don't have as many vibrational modes that they can relax through, right? So we have less energy loss to those non-radiative transitions. Right, so that means more fluorescence. The textbook has the structures of phenolphthalein and fluorescine in it. Phenolphthalein has 3 phenyl groups, but they're all sort of free to rotate, right? Those 3 phenyl groups are not connected to one another. They can rotate around. And so phenolphthalein is really not fluorescent at all. But if we look at fluorescine, fluorescine has 3 fused phenyl rings together and another phenyl ring that can spin below it. But those 3 fused phenyl rings are a very rigid system. And so fluorescine, as we talked about last time, has a quantum yield of 0.89, I think, something like that. And so, you know, fluorescine, a very fluorescent molecule. Okay. And so sort of as a rigid and conjugated don't always go together, but often they do. And conjugated molecules are just molecules where usually that pi to pi star is a very small delta E, right? Pi and pi star closer together. If you did take PChem2, think about it like a particle in a box, right? You probably talked about conjugated molecules as particle in a box anyway. The longer the molecule, the lower those energy levels, right? And so the more conjugated your system, the closer together those energy levels are, the easier it is for that pi to pi star transition. This series here with heteroatoms, these heteroatoms have, rather than pi electrons, in electrons, so they're not part of conjugation, right? And so when I say heteroatoms, you know what I mean? Yeah, not carbon and hydrogen. And so if we have something that's already conjugated, so it has a pretty low pi star energy level anyway, and it has a heteroatom that has those in electrons that aren't part of the conjugation, then you end up with these into pi star transitions, and those transitions are often low enough in energy that we can see fluorescence from them. And so having a heteroatom in our cycle can lead to increased fluorescence as well. This series here quinoline and isoquinoline are fluorescent. Pyridine is not. The current theory is that that this converts quickly to a triplet state. That the pi to pi star transition is once it's excited, it converts quickly to a triplet state. And what do triplet states do?
Phosphorus.
Yeah. So pyridine phosphoresces. That's a fun word to spell. Okay. And of course, we want to reduce the amount of self-quenching. We talked about quenching molecules last time as molecules that have that the ability to once our atom of interest, fluorophore, once our fluorophore is excited, you know, collision with a quenching molecule can steal that energy, so it doesn't fluoresce back out. And so there is self-quenching, where a molecule of the fluorophore can collide with another fluorophore and steal some of that energy. And so both of them have sort of not enough energy for a photon, and so they just relax back down to the ground state. And most of that is due to concentration, right? Because it's collisional, we want to have low concentration of those quenching agents, even if it's self-quenching. But having too many sort of crazy functional groups can also lead to self-quenching more readily. And so our textbook provides a picture of nitrobenzene versus aniline. Nitrobenzene doesn't fluoresce, but aniline does, because nitrobenzene has sort of that bulky NO2 group that A, isn't very rigid, and B, lots of heteroatoms, the nitrogen and 2 oxygens. Those electron, that part of the molecular orbital can steal energy from other already excited fluorophores very easily because of those low energy into pi star transitions. They can just, you know, any collision, they'll transfer some energy. So those four pieces are really what contribute to fluorescence in a molecule. And so be able to, you know, think through whether or not a molecule has one or more of those characteristics as to whether or not it'll be fluorescent. All right, instrumentation for fluorescence. We talked a little bit about this on Tuesday in lab, right? So in a very simple fluorescence instrument, right, we had our light source. And what did you notice about the geometry of the source and the detector from Tuesday's lab?
The source isn't pointed directly at the detector.
That's right. The detector would not be over here, right? The detector is going to be, we call it orthogonal, right? Orthogonal in mathy terms just means perpendicular, right? And so if our source is here, it's going to shine on our sample. And then we're going to measure that fluorescence in our detector. Oops, I messed out. We need a monochrometer first. And so this is our this is what our simple sort of LabQuest unit looked like. But what was special about the source in LabQuest? What was it?
You had 3 different light source options,
We did. What was different about them?
different wavelengths.
Yeah, different wavelengths. And so in the LabQuest version, these were single wavelength sources, right? LEDs in the LabQuest version. What's the other single wavelength source that we've talked about a little bit? Maybe not enough for you to remember. Lasers have just a single wavelength. Right? So in our LabQuest, it's a simple version. It's only got a single wavelength for excitation, and what we measure is absorbance. What we measure is emission. Right, and so for this one, in this setup, we can only measure emission because of that single wavelength excitation. In sort of research grade fluorimeters is what they're called. In a research grade fluorimeter, you have your source. Oh, I shouldn't write too close to the bottom, it freaks out. Ugh. And then because we want to measure both the emission spectrum and the excitation spectrum, we need to select our wavelength or be able to change our wavelength of the source. So we have a monochromator here that then goes into our sample. And our sample gives off light in all directions. What do we call that?
Isotropic.
Very good. That light gets collected and focused into our monochromator. And then to our detector. Right. And so now with dual monochromators, we can perform both an excitation and an emission experiment. And so if we think back to that, the diagram we had that was looking at the anthracene fluorescence, right? We had an emission spectrum, we had an absorption spectrum that looked something like this. I don't remember exactly. And then an emission spectrum that looks something like this. This down here would be wavelength, not energy. Ugh. So this is emission. This one here is excitation. All right. So you can think about a little bit, which monochromator is fixed and which monochromator is scanning for emission, and which monochromator is fixed and which monochromator is scanning for excitation. Right? You can expect a test question related to that.
Dr. Davis, I have a quick question.
Sure.
What was it called, the light called that came out of the sample that went in all different directions?
The fact that it goes in all different directions, it's described as isotropic.
Gotcha.
the sun, for example, is an isotropic light source. Right? It gives off light in all different directions. We on Earth are just receiving a small fraction of the sun's radiation. And it still gets really hot. Okay. All right, so I'll just put here, think about monochrometers. Okay. All right. So that's our main instrumentation. I won't go into a whole lot of detail here. The monochrometers are the same type we use in UV-Vis. The detectors are the same type we use in UV-Vis. The sources are the same type we use in UV-Vis, as long as we're talking about the dual monochrometer setup. If we're talking about the cheaper monochrometer setup, the single monochrometer setup, then of course that source has to be single wavelength. And so either LED or laser. But here we can have whatever the UV-Vis sources were, could be a source for fluorescence as well. So the actual nuts and bolts of it aren't that different. It's just this difference in geometry. So this is sort of what I was getting at earlier. We have, with dual monochrometers, we have the opportunity to take different kinds of spectra. We can take that fluorescent spectra, I call this an emission. That's the same thing, right? Fluorescence is a type of emission. So you can take excitation spectra, fluorescence or emission spectra, and then absorption spectra, only if we have a way to bypass that first monochrometer, right? We need all wavelengths of light in order for us to do that. Or you can have your monochrometers track, so they're both on exactly the same wavelength as you go through the scan to get absorption. Okay. And so this slide is essentially kind of what I want you to figure out for the exam, right? For emission, which monochrometer is fixed, which is scanning, right? Ditto for excitation. And then I'll go ahead and tell you, for absorbance, if we're in a double monochrometer instrument, both monochrometers have to track at the same time. And I'll put here same wavelength. Right. So think about these two questions for emission and excitation for the exam. Also think about what wavelength it's fixed at. Okay. All right. And again, I mean, this is in our text. You can find it online. Just think through it for the exam. You probably have already thought through it, maybe. Okay, so issues with polarimetry, right? There are some, and so we have to take these into account. The first two are issues that are largely corrected with software that's built into the instrument, and so you as a user don't really have to think about it a whole lot. the first is the detector correction. This is a correction that we also have to take into account in UV-Vis, but in UV-Vis, we usually have more than enough light to see what we're doing, right? We don't use UV-Vis on super concentrated solutions so that there is, because they start to deviate from Beer's law long before this is an issue. In fluorimetry, because we're measuring against a black background, we're looking at very little light to begin with. And so this detector correction, we have to take into account how efficient our detector is. That's not a word. At various wavelengths. Right. I think we talked a little bit when we talked about the detectors and those photomultiplier tubes, how you have to choose a dynode material with a low work function. Remember, work function is the energy required to get an electron off of a piece of metal when a photon hits it, right? And if we're looking at a very wide range of wavelengths, that metal may have different work functions for different wavelengths, and so you have to take that into account. Again, software usually corrects for this, but we don't need to worry about this in UV-Vis because we have an abundance of photons. We're sure that we're going to detect something. In fluorescence, we're not always sure that we're going to have a super excess of photons. Another one that we have to do that we have to worry about a little bit are the source intensity fluctuations or corrections. Right. This is one that we do worry about a little bit in UV-Vis, but in UV-Vis we always take a background, right? A background in fluorescence only helps us if whatever our solvent is also fluoresces. And again, the kind of experiments that we do in fluorescence, we're looking at very small concentrations, or we're tracking cells. We've tagged something biological with a fluorophore. We're not usually working in solvents that are fluorescent. We're working in water. We're working in alcohol, maybe. We're not working in isoquinoline, or we don't have a solvent of fluorescein, right? These are not things that we have. And so in UV-Vis, we correct for this source intensity differences. So our source has different powers, different intensities. At different wavelengths. Right? And in UV-Vis, we take care of that by taking a background scan. Right? We do that background scan and we see, okay, the power's high here, power's low here, then the power goes back up, it goes back down, or whatever, however the power curve for that particular source looks. In fluorescence, we don't do a background, really, because we assume that the background is zero. Since we're measuring orthogonal, there shouldn't be anything. And so usually, again, the instrument has some calibration already built in for the light source. That, okay, I know this is a xenon bulb, and here's the power curve for it, and so I have to adjust at different wavelengths. So those two lights that are largely taken care of by the instrument, and we don't worry about them too much. The ones that we do worry about are concentration issues or high absorbance. if you look at the picture here, this figure, in the first cuvette, we have a relatively low concentration rhodamine B, right? So these are, as we go from left to right, these are increasing concentration. The one on the left, we have the same fluorescence throughout the cuvette, and so we should see, we shouldn't have any concerns there. Think about the fact that even though the cuvette is a centimeter wide, remember that the detector is often looking at just a piece of that, right? And so we're looking at maybe a box, you know, a couple millimeters on a side. That's where our detector is actually looking. And so if we draw that box on all of these, you can tell that by the time we have higher and higher concentrations, what's happening is all of those photons are being absorbed very quickly because our concentration is so high, and they're fluorescing where they were because the lifetime is pretty short. They don't move a lot between absorption and emission. And we're not detecting any fluorescence, but not because the concentration is too low, but because the concentration is too high. This is called the inner screening effect, or inner filter effect. And so all the photons are absorbed at the edge of solution. But fluorescence is detected in the middle. There are some fluorimeters, they are not cheap, but there are some fluorimeters where you can measure the fluorescence. So if this is our cuvette, this is a top-down view of our cuvette. Right, here's our source, our excitation wavelength out of our monochromator, hits here. And then based on you know, the refractive index of your material, there's an angle at which some of that light will bounce off. Right? And you can measure, sorry, an angle at which none of the light bounces off. We don't want our excitation wavelength. And so you can measure the emission at a front angle. Right? Again, because that fluorescence is isotropic, it doesn't matter where a detector is really, as long as we just don't put it exactly opposite the excitation. Right? And so this front angle fluorescence is really the only way to deal with a very concentrated solution where you don't get fluorescence all the way through. The last one to talk about is photo bleaching. And this happens when we have just a long enough lifetime that most of our molecules end up staying in the excited state. Right? We don't get it, as soon as they go back down the ground state, they're re-excited. And so we don't get a lot of fluorescence. Right? The light hits it and it absorbs a photon, but it kind of stays in that excited state. And we don't ever get the opportunity to just see the fluorescence. Right? Sometimes also, if we absorb a photon, it can actually change the nature of the molecule. And so eventually it just doesn't absorb photons anymore, right? Think about, I don't know if you ever had those color change t-shirts as a kid. Right? You wear them out on the beach, you wear them out in the sun, and they were white before and they turned crazy colors. But after you washed them 7 times and wore them all day for a month, they weren't quite as vibrant after a month of wearing them, right? That's because the dye molecules that are in there aren't as good at absorbing as they were when they were first put on the shirt. That's another example of photo bleaching, but kind of in the opposite direction, right? And so photons change the molecule to where it doesn't absorb as efficiently, or sorry, it doesn't fluoresce as efficiently. Well, it could not absorb either, but it could also be that long lifetimes means that it sort of stays in the excited state. All right. The last thing in chapter 8, any questions on that? Okay. The last thing in chapter 8 are other sort of ways that we can use fluorescence. Right? The first one is chemiluminescence. Right, these are chemical reactions that are exothermic, but instead of giving off heat, they give off light, right? They get rid of excess energy, not as heat, but as light. And so, of course, we all know about fireflies, right? That's a classic chemiluminescent reaction. But there are others out there. If you are a fan of TV crime dramas, you know that they use luminol to look at blood on crime scenes and things like that. That's another classic chemiluminescent reaction. And so we can look at that in a fluorimeter, just like we can look at other things. Of course, with chemiluminescence, we could look at it in a normal UV vis. Because we're not exciting it with light, we're waiting for the chemical reaction to occur. We just need to detect it. It's in this chapter because this chapter is on luminescence rather than absorption. Another useful technique is Forster resonant energy transfer. This is called FRET. And think about this as sort of useful quenching. Right? That's what this diagram is here for us. We have one protein that has a cyan fluorescent protein bound to it. Light comes in, that cyan fluorescent protein absorbs it and re-emits it, right? So we know that cyan fluorescent protein works, that it actually is in our solution. However, we've got another protein with yellow fluorescent protein tagged to it that absorbs at a different wavelength, right? So cyan fluorescent, yellow fluorescent, likely going to absorb it in different places. And what happens is if those two proteins are close enough together, right, look at this distance versus this distance, right? If those proteins are close enough together, then the yellow fluorescent protein will quench the cyan fluorescent protein, right? Yellow is lower energy than cyan, like blue. And so in that quenching, even though it loses energy in the quench, it's still enough energy for the yellow fluorescent protein to fluoresce. Right? And so this is a way for us to measure sort of the distance between two different proteins. So we can see if we're getting only, cyan fluorescence out, then we know that our two proteins aren't mixing very well, for example, or they're not interacting with one another. Or maybe we've actually tagged our substrate with one and our protein with the other, and we want to see if they're docking, right? The closer they are together, the more we're going to get fret, and so the more we're going to get the emission from the receiving fluorophore. So that's a neat technique. It's a very biochemy kind of technique that's used to tag proteins and other biologically relevant molecules. There is also a phosphorescence spectroscopy. And of course, in phosphorescence, we want to measure, we want to make sure that we are, we want to make sure we're getting only the phosphorescence. We don't want fluorescence, and we don't want the light from the original light source. And so in a phosphorescence experiment, you have your excitation wavelength. So out of our source and out of our monochromator into your sample. The samples are usually cooled with liquid nitrogen. At lower temperatures, those lifetimes get longer. And so if we want phosphorescence, then we want to cool it down. So this is usually cooled to liquid nitrogen temperatures. And then it goes out to a detector, well, monochromator and detector. But what's interesting is what happens around the sample, right? There's a chopper. Ooh, I'm going to be real bad at drawing this. There's a chopper that they kind of look like bow ties, in my opinion. Right, there's one. And he's before the sample, rotating this way. And there's another after the sample that's orthogonal to him. Ah. Right. And he's also rotating. They're rotating in sync with one another. And so I'm going to use my hands as these shutters. And so the sample is down here at the bottom. Light comes into the sample and it excites whatever's in there. And as these turn, this one cuts off the light, and so it can fluoresce a little bit. And this one opens it up so that after fluorescence is done, only phosphorescence reaches the detector. Right? And then it rotates back so that it doesn't rotate back, but it goes in a circle, but my hands don't. So that light can hit the sample again, excite it. We do our fluorescence while it's dark, and then only phosphorescence reaches the detector. Right? And so as those two bow ties sort of spin, we get this period of dark and then phosphorescence, and then dark and then phosphorescence, and then dark and then phosphorescence. That's just kind of a neat little bit of instrumentation. Okay, that's it for chapter 8. That's it for exam 2. I promised to have exam 1 grades up over the weekend. Those would be nice to know, yeah. So I'll put those up over the weekend. I've been working on grading them, but I'm not quite done yet. Any questions about chapter 8, chapter 6 and 7? Savannah has a question?
I just have a question about my specific lab stuff, but I can ask later.
Okay.
Can I ask after class?
Yeah, that's fine.
Okay.
We also have lab questions.
Okay. Well, if you want to hang around, you can. If you want to schedule a time later, you can. But that's it for lecture today. Let me chat here with Savannah. If you're done, bye-bye.